Assalamualaikum warahmatullahi wabarakatuh and greetings to you. My name is Nur Izzah binti Zainal Rashidin and I'm a third year undergraduate in Mathematical Sciences from University Technology Malaysia. I hope you are ready to get down to business to discuss a research proposal of topic that is important to all of us, application of finite difference method on water pollution simulation. I've put together an agenda for today's presentation. I will start with a quick introduction, then I will dive into literature review. Next, we will review both of the research methodology and expected findings. And finally, I will wrap up with a conclusion. As for the introduction, world-renowned oceanographer Jacques Cousteau once said, "Water and air, the two essential fluids on which all life depends, have become global garbage cans." This quote leaves quite a mark in my heart, since two of our three basic resources, including soil, are very dear and precious to any humankind. It is undeniable that our source of clean water is widely affected by water pollution. The water pollution occurs when the contaminants are discarded into the affected areas without carrying out screening tests and treating it first. Polluted water has been a part of our life unconsciously, not only here in our beloved country, Malaysia, but all around the world. Illustrated in the Figure 1 surveyed by the Ministry of Natural Resources and Environment (NRE), published by the Department of Statistics Malaysia. 2016 is the starting year of the river pollution increment in Malaysia, followed by the highest case in 2017 compared to the rest of the year from 2013 till 2019. This indicates how serious water pollution is in Malaysia. As for background and scope, in a general sense, the sources of pollutants are from the sewage ejected into the river, industrial waste discharged into the water without any pretreatment, and the minor or major landslides resulted from the uses of poisonous agricultural substances such as chemical fertilizers, insecticides, pesticides, nitrogen, bleach, and manures. Not only that, there are also uncontrollable water pollutants that are sourced from within the river itself, like the toxins released by the bacterium. Naturally, most of these pollutants contain heavy metal and other dangerous chemical substances that are difficult to be expelled from the human and animal body. The presence of these pollutants will only cause difficulty and insecurity for people to drink water, produce food, bathe, for recreational purposes, and for domestic use. Problem statement. On account of the fact that water is a basic necessity for every living thing in this whole world, any individual's demands for clean and quality-tested water to cope with their daily life routine, poor sanitation, and contaminated sources of water will only lead people to be having complications in various diseases. Therefore, encouragement to adopt drastic strategies to tackle this issue should be executed by the Malaysian government in order to ensure the safety of water supply. In this study, the analytical solution was compared with the numerical solution in case the dispersion is proportional to the same linearly interpolated velocity. Research objectives. Next, moving on to our next agenda, which is research objectives. The objectives of the research are to govern the water quality pollution level study using a finite difference method model and to obtain the least absolute error by conducting a finite difference method. I hope that all the objectives written above will be able to be accomplished with a thorough survey and research, followed by the research questions that we will discuss in the next subtopic. I believe that the questions will be of aid to us in conducting this research while obtaining the research objectives. Research questions. The research study will be conducted by identifying the concentration of the water pollutants with respect to distances, and that will determine the variables which could become potential predictors of water pollution. Hence, the study deals with these following questions. What is the relationship between the time and the concentration of water pollutants? Which linear variables, time or distance, can be a good predictor for the concentration of water pollutants? And the last question is, what are the incentives for every individual to reduce the water pollution as well as to improve the level of the water quality? Literature review. This case of study summarizes, compares, and critiques the most relevant scholarly sources on the topic. Key concepts, theories, and studies. This study proposed a one-dimensional advection diffusion equation to predict water pollution concentration transport. Numerical modeling is performed to predict water pollution concentration transport. The implicit finite difference method is used to approximate the advection diffusion equation. For simulation purposes, the boundary and initial condition, spatial and temporal steps, and approximations of the advection diffusion equation were encoded from. The results of the one-dimensional advection diffusion equation were successfully used to predict the water transport pollution concentration by manipulating the velocity and diffusion parameters. key debates and controversies. There are many techniques that can be applied to the water transport problem, including experimental and numerical models. Numerical modeling is considered to be more viable than the experimental model because the parameters can be easily adjusted, which makes it easier to handle in the industrial side. The advection diffusion equation is one of the most important partial differential equations that have been used in pollutant transport. A suitable numerical method can be efficiently and quickly provide accurate information about the contamination concentration at different times and places. Therefore, many researchers have studied the numerical methods to solve the advection diffusion equation to predict the water pollution problem. The finite difference method was used to solve the flow equations to obtain the flow velocity and flow direction of the water pollution concentration. In this study, the finite difference method is used to solve the one-dimensional advection diffusion equation as it is able to predict the concentration of pollutants. Gaps in existing knowledge. In order to approximate the advection diffusion equation, the implicit Crank-Nicolson should have been used instead of finite difference method. This can be done by averaging their values at time step j and j plus 1. The reason why the implicit Crank-Nicolson should have been used is because of its higher precision and accuracy final result compared to the finite difference method. This can be proven based on the validation in error estimation of the numerical scheme that we will discuss in the agenda expected findings. Research methodology. Quantitative researchers usually base their work on the belief that facts and feelings can be separated, that the world is a single reality made up of facts that can be discovered. The design of this study was primarily quantitative in nature as the generated case study is based on numerical data collection and analysis. In addition, quantitative research is confirmatory and deductive in nature. The ideal study in the quantitative tradition is the experiment. Data analysis is primarily statistical and involves an analysis of variables such as pollutant concentration, time and distance from a given area. Hence, for this study, the purpose is to govern the water quality pollution level study by using a finite difference method model and to obtain a least absolute error by conducting a finite difference method and sources. In this subtopic, we will also present the algorithm for the numerical solutions involved. First, we need to govern the equation as a water pollution model by applying the advection diffusions as the following, where C is the concentration at the point X at the time t, D is the diffusive constant in the X direction, U is the fluid velocity, and T is the time, with appropriate initial and boundary condition. Numerical methods for governing equation. In mathematics, finite difference methods are numerical methods for approximating solutions of differential equations using finite difference equations to approximate derivatives. A finite difference method assumes that the derivatives in the differential equations are replaced by the finite difference approximations. This gives a large algebraic system of equations to solve instead of the differential equation, something that can be easily solved on a computer. Explicit-centered difference scheme. In order to develop the scheme, we discretize the xt plane by choosing a mesh, width, space, and a time step. The finite difference methods we will develop produce approximations to the solution at the discrete points by the following. Simple approximations to the first derivative in the time direction can be obtained from the following. Centered difference discretization in partial derivatives is as follows. The discretization is obtained from second-order centered differences in space, and then we obtain the following difference methods. To find the numerical solution of the model, we need to accumulate some variables which are given in the following algorithm. As for input, nx and nt are the number of spatial and temporal mesh points respectively. Output, CST, the solution matrix, and initialization. Step 1. Calculation for concentration profile of explicit centered difference scheme by creating loop 4 to avoid tedious working. Step 2. Output CXT. Step 3. Figure presentation. And Step 4. Stop. Expected findings. Practical implications. We will review the numerical results, result and effect of water pollution transport on velocity and diffusion rate, as well as the error estimation of the numerical scheme. In this section, the numerical simulation results at different times and positions are illustrated. Consider the initial concentration C0x equal to 0 and the constant boundaries value CT0 equals to 1 and CT100 equals to 0. The concentration profile is demonstrated in figure 4.1, considering the concentration distribution at different time, distance, and concentration parameters. The curve marked with solid line show the concentration profile for 4 minutes, and the visible curve with dotted and dashed line represents the concentration profile for 8 minutes. The curve solid line red shows the concentration profile over 12 minutes, and the curve visible through dashed line represents the concentration profile over 16 minutes. The dotted line curve shows the concentration profile over 24 minutes. We have seen the concentration of pollutants increase over time. In figure 4.2, the curve marked solid line blue shows the concentration profile for the initial position, and the dotted line curve shows the concentration profile for 6 meters. The curve marked by dotted and dashed line shows the concentration profile for 12 meters, and the apparent solid line curve represents the concentration profile for 40 meters. The curve marked by dashed line shows the concentration profile for 100 meters. It has been found that the concentration of impurity increases with time in a fixed position, result in effect of water pollution transport and velocity and diffusion rate. Figure 4.3 shows that the concentration distribution profile at t equals to 24 minutes was calculated by increasing the velocity rate values from 0.01 meter per second to 0.05 meter per second, and the value of diffusion rate from d equals to 0.05 meter squared per second to 0.25 meter squared per second. Figure 4.4 shows the pollution concentration movement tends to spread faster than when the velocity and the diffusion rate is high. Besides that, the concentration of pollutants also decreases as it travels further along the distance of a certain area. Figure 4.4 shows the concentration distribution for each velocity rate at 24 minutes. The velocity varies at rate 0.01 meter per second to 0.05 meter per second. Figure 4.5 shows that even though the diffusion rate remains constant, the concentration of the pollutant spreads faster by increasing the velocity rate, d equals to 0.5 meter squared per second. This is the same as when we fix the value of diffusion rate and varying the value of velocity rate. The result gives a faster rate of spreading of the pollutants on the water contents. Figure 4.5 shows the concentration distribution for each velocity rate at 24 minutes. The diffusion rate varies at d equals to 0.05 meters squared per second and 0.5 meters squared per second. Figure 4.4 shows that when the diffusion rate is high, then the pollution spreads faster while the velocity rate is kept at constant rate. As previously discussed, even if the velocity is constant, the spreading of the pollutants is faster with a higher rate of diffusion. Based on figure 4.3 and 4.4, the results shows that when the two important parameters, velocity and diffusion rate in transport of pollutants, vary, the spreading of the pollutant will be affected. As a result, the water pollution concentration transport with higher rate of velocity and diffusion will spread faster than the lower rate. Error estimation of the numerical scheme. In this section, the forward time-centered partial numerical solution is validated with the analytical solution. Figure 4.6a, Figure 4.6b, and Figure 4.6c show the error of the numerical solutions to this problem when compared with the analytical solution for delta x equals to 0.05 and delta x equals to 0.025. From Figure 4.6a, Figure 4.6b, and Figure 4.6c, we can see that the absolute errors for the forward time-centered space method is decreasing as the time step size decreases. Conclusion of study. In this study, the variable analysis were conducted between the concentrations of the pollutants, distance, and time, as well as other monitoring elements separately. The results showed that the concentration of the pollutants had an obvious relationship during the same period. Therefore, a model of finite difference method was governed. Limitations and future work. There are several potential limitations in this research study. First, we only considered a few variable analyses such as concentrations of the pollutants, distance, and time involved in a certain area instead of other possible variables like the temperature of water, the pH level of the water, the rate of population growth of aquatic organisms, etc. The reason is mainly to focus on the current concentration of pollutants that will be a disturbance to the river population. On the other hand, our mathematical method is also limited to finite difference methods only. Based on the validation in error estimation of the numerical scheme in section 4.1.3, the forward time-centered spatial methods gives a higher relative error compared to the Crank-Nicolson method. In other words, this proves that the Crank-Nicolson method is better than forward time-centered spatial method due to its higher precision and accuracy. Therefore, for future work, it is suggested that various variables, if any, are considered, which are the temperature of water, the pH level of the water, and the rate of population growth of aquatic organisms in the chosen regions, so that more comparisons can be made. In addition, further studies can use many kinds of data and mathematical methods to predict air pollution. The following are the list of references that I used while preparing this research proposal. Thank you.